So in this video and onward, we're going to be looking at some different types of reaction mechanisms. And what's going to be really important here is the concept of arrow pushing. So it's still giving you some trouble. I'd highly recommend making sure you brush up on arrow pushing and how to correctly do it, because it's going to be important from essentially this part of the chapter and for the rest of the semester. We're probably going to be doing some form of arrow pushing in every single video after this. So the first reaction we're going to look at today is the SN2 reaction. And what that stands for is substitution, nucleophilic, and bimolecular. And so we'll get into each of those terms in just a second here. But the general scheme for an SN2 reaction is as follows, right? And we're going to be using some terms that we've covered in previous videos, including nucleophile, right, an electron-rich species, which we can already tell is our hydroxide ion, right, because it has a lot of electrons to give, especially because of that negative charge. We have our electrophile, an electron-poor species, and we can see, right, because this halogen here that has a dipole moment, right, partially negative chlorine and a partially positive hydrogen, we know that our carbon species here is the electrophile. And so what that leaves us with now is this new term, a leaving group. So this is a species that leaves with a pair of electrons that was once bonded to the electrophilic species. So that leaves us with chlorine here as our leaving group, Lg, leaving group. And we can see the result of that in the reaction, right, in the products, where we have our new species, right, the nucleophile, attack the electrophile, and then we have our leaving group, which left with its pair of electrons, right? Of course, chlorine, I'll zoom in here to sort of emphasize, right, has these 3 lone pairs, and now it has 4, right? Because that covalent bond, which of course is 2 electrons, it took that with it when it left. So in an SN2 reaction, this all happens simultaneously. So we have bond forming and breaking all at once through something called a backside attack, which we'll get into in a little bit for what that exactly means. But essentially, we have our nucleophile, right, attacking our electrophilic species, and the covalent bond holding the leaving group, right, represented by L here. That covalent bond is breaking onto the leaving group, giving us our final products here. So there's bond forming and breaking all at the same time. So these 2 arrows are happening all at once. And when we're looking at this, we can define electrophile and nucleophile in a few different ways. The first thing that we want to look at is something called rate law. And so for an SN2 reaction, it depends, the rate law depends on the concentration of the electrophile and the nucleophile, right, in a reaction vessel. Right, and K is our rate constant. The electrophile, in this case, is this chloroethane, and then our nucleophile is the hydroxide ion. And so what this means is, right, the SN2 reaction depends on the concentration of these 2 species, right? They're both important, okay? Which might seem kind of obvious when I'm saying this, but this will matter in a future video for a different reaction, right? But that's why it's called bimolecular, because the reaction depends on the concentration of both the nucleophile and electrophile, okay? And just so the arrow pushing here again doing this backside attack, we form our products here, right? And so why are we doing this backside attack? Why is this the method it goes through? And it's important to recognize, thinking back to our molecular hybrid orbitals, right, back from chapter 1, right, that covalent bonds, right, we know is a sigma bond, right? But if you remember, we had an anti-bonding orbital too that was higher in energy. And so what's happening there is, right, we have this sort of general framework for the anti-bonding orbital, right, where we have that node in the middle. And so what's happening is when this actual attack is going on, right between when we attack the carbon and break that carbon-chlorine bond, our hydroxide anion, right, has that same phase lobe that will end up filling, right, the anti-bonding orbital, right, from the back. And that's why it's always a backside attack, right? And more specifically, right, if we try doing the arrow pushing, right, and showed it attacking here, right, in between the carbon and chlorine, there's a lot of electrons there, there's a lot of electron density, so the hydroxide ion likes to come in from where there is the least amount of electron density, okay? So it's filling up that anti-bonding orbital. If nothing else, at least remember that the SN2 reaction happens through a backside attack, okay? So what we're going to look at now is a reaction diagram, right, an energy diagram, to sort of drive home some different processes happening here, right? So remembering that this is our reaction scheme, what we have here, right, is we have our reagents, which are higher in energy, and our products, which are overall lower in energy, right? And this is important to recognize, right, because this reaction is sort of happening spontaneously, okay? And so we can illustrate that through a diagram. So what's happening is, for this SN2 reaction, we need to have a sort of activation energy, right, to make the reaction go. And then we get lower in energy when we get back to the products. And so what this all means is that the reaction has a sort of flow to it, if you will, where there's a difference in energy, right, which we can define as this G term, which is Gibbs free energy. So this delta G naught term, right, and that is the free energy of the reaction, okay? And what we see here, right, this is a negative Gibbs free energy, right? The products are lower than the reagents, meaning that it is exergonic, right? It happens spontaneously, right? Energy is released. However, there still has to be some sort of initiation, right? This has to go over a sort of energy hump to get down to the products. And that term is this transition state energy listed down here, right? The free energy of activation, the energy it takes to get the reaction to the transition state. And so what does this transition state mean, right? What's happening here? So the transition state is the highest point in the diagram. And you might see it kind of labeled as EA, which again means activation energy. And so what's happening in that state is the electrophile is being attacked by the nucleophile. And so we're seeing that transition, right? Because before, right, on the previous page, I showed arrow pushing, right, to get from reagent to product, but what's happening in the middle? What's that middle phase look like? And so that's what we examine in the transition state. And so it looks something like this, right? We have to draw it 3D spatially, right, where we have our CH2 bonded to the carbon down here, right, the CH3, so that's what this is, okay? And we have chlorine, right, which is attached to the carbon, but we also have OH, right, that hydroxide, which is becoming attached to the carbon. So what we're showing in this transition state is the simultaneous forming and breaking of a bond, right, represented by these dotted lines. And this term here just means transition state, okay? So we're showing bond breaking, right, with that carbon and chlorine, and bond forming. And we can further illustrate that by showing partial negatives, right, on these two different groups, right, because the chlorine, as it's breaking, is getting a negative charge, And the hydroxide anion, which is negative to start with, as it forms to the carbon, right, as it's forming that covalent bond, it's losing the negative charge, right? So we say it's partially negative. And this transition state, you also probably notice, I've said it so many times now that carbon shouldn't have 5 bonds, but here it looks like it has 5 bonds, but that's not totally true, right? Because there's a bond being broken and a bond being formed. Right, so these are both partial bonds, right? Again, as illustrated by these dotted lines. So this transition state is really important to consider when we're going through these SN2 reactions. And this is, again, the highest point energy for this reaction, right? And it makes sense too, because it's kind of a clustered molecule right now, right? We have chlorine leaving and hydroxide anion coming in. And this plays a big role too, right, this transition state, in determining stereochemistry, right, which we now always kind of have to be aware of, right, because again, because this molecule is going through a backside attack, right, the lone pair of the nucleophile attacks the antibonding molecular orbital of the electrophile, leading to an inversion of configuration, right, and I will illustrate that here to sort of show what's going on. So right now, this molecule, right, and I'll let you do this yourself, but this has a S configuration. And when we do the attack of the hydroxide anion, right, we have to have the arrow pushing coming from behind to that carbon, right, that backside attack. Right, and then the chlorine gets those electrons afterwards. And so what's happening here is now the hydroxide, or now the alcohol group, is on the other side of the carbon. Right, you see that? Well, at first, all these substituents here kind of look like they're pointing towards the left, and after the hydroxide anion comes in and attacks here, everything gets pushed to the right. The wedges and dashes and the in the plane ethyl group don't change, right, but they're getting pushed to the other side. And actually now, the configuration of this molecule is R. What's important to note here, right, I've said this before, that S and R are just arbitrary naming terms, right, to give a chiral carbon something. But because the hydroxide molecule and the chlorine groups are #1 priority, right, for both of these molecules, right, everything else is carbons, right, when this comes in and pushes everything over, we get the R configuration, right? If this hydroxide anion was a chlorine and it came in, right, we'd still get that inversion. Right, it would still go from S to R. Right, so it's important to keep in mind that the priorities still matter for naming these things, but it's a helpful tool in sort of visualizing the inversion of configuration happening. And again, just to drive this home, if we were to look at the transition state for this molecule, or for this reaction scheme rather, right, we have our ethyl group here, which I'm going to note as CH2, CH3. We have the bond breakage of chlorine. Oops. We have the bond breakage of chlorine and the bond formation of the hydroxide anion right here. Right, and we denote these with a partial negative term. And so you can see, right, that while one side gets pushed out, the other side comes in. So like, right, looking at this transition state like this, right, we can practically see the chlorine bonds leaving, right, and then on the other side, right, when the hydroxide anion comes in, we can see that inversion of configuration taking place, right? We can almost sort of block out, right, one side of this transition state to sort of see what's happening here. Right, where initially we had, right, this molecule, essentially, and then now on the other side, right, when this chlorine leaves, and all left is the hydroxide anion, we have our final product. Right, you see that? Hopefully that makes sense. And so, of course, right, because of this transition state, and because of the size of the carbon mattering here, this is also going to affect the rate of the SN2 reaction. So if we start comparing SN2 reactions, we can say which one is faster and which one is slower. Right, because the smaller this carbon is, right, if it was just a methyl carbon, right, with just hydrogens attached to it and a chlorine, this reaction would happen very quickly. Right, so for carbons with just a methyl group, the reaction is very fast, but a tertiary carbon would be very slow. Right, so a carbon with 3 other carbons attached to it, and a halogen would be pretty slow, but a carbon with only 3 hydrogens and a halogen would be really fast, right, because of the steric hindrance of the groups on the carbon, right, makes this reaction slow, right, so steric effects of substituents makes the rate slower. Okay, so what we'll do in lecture together now is do a couple of, or several rather, problems where we're going to look at some different reactions and predict the products using arrow pushing, right? And we're also going to look at some different substrates, right, some different electrophiles here, and determine which would react faster in an SN2 reaction.